Okay, so good evening, everyone. Welcome to the fifth live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for this course for the entire course duration. So, for those who have joined for the first time for the live session, so these doubt clearing and interactive sessions they are held every Tuesday from 6 p.m. to 8 p.m. And during these session, we interact by answering to the questions that I will ask in the chat box by posting your questions in the chat box or by raising hand and muting and asking your queries. Apart from the class, you can use the discussion forum of the course where the questions will be addressed through the discussion forum itself or in the next live session. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So, in today's session, we'll first revisit the last live session that was for week 4 content, just a quick recap, and then we'll look through the things that was covered in the week 5 content. So, the week 5 content that we will discuss today is about mixture design of concrete, which is divided into following subsections for the discussion that we will have today. So, first we'll have an overview of mixture design, then we will talk about target mean strength and characteristic compressive strength. We'll talk about IS 456 and IS 10262 based mixture design, and we'll see DOE method of mixture design. In between, we'll have some numerical questions also related to mixture design and few objective questions. So today the theory part won't be much, but the application of theory part will be more. That we will deal in the questions, and we will look more into the codal provisions, like how code describes a mixture design. Finally, we'll conclude the discussion, and I will try to address any other queries post discussion. So last week we concluded the fourth week of the course where we talked about mineral admixture used in concreting. Mineral admixtures is also known as supplementary cementitious materials and are used as a partial replacement of cement to promote sustainability and improve strength and durability. We saw production of some of the most commonly used SCMs like fly ash, ground granulated blast furnace slag, and silica fume. Then we talked about characterization of SCMs to understand why SCM is reactive and how they differ from one another. In characterization, we saw SCM images, particle size distribution, fineness, and specific gravity of mineral admixtures. We talked about chemical compositions of mineral admixture to understand how they differ from OPC and which proportion makes them as a reactive supplementary material. We saw different testing methods to evaluate reactivity of a mineral admixture, which were pozzolanic activity index testing and lime reactivity testing. We talked about hydration of pozzolana and pozzolanic reaction, how this pozzolanic reaction contributes to the betterment of concrete by consuming lime, by refining pores and interface, by slowing down the rate of reaction and lowering the heat of reaction in parallel to promoting the sustainability, and how this pozzolanic reaction can be accelerated by alkalis and gypsums. We talked about effect of mineral admixture on fresh properties like setting time. So we saw fly ash due to its ball bearing effect delays setting, while silica fume due to high surface area accelerates setting. Same reason then applies for water demand and SP demand also, where fly ash reduces water and SP demand, while silica fume increases water and SP demand. In terms of hardened properties, we saw fly ash and slag. Due to their slow reactivity, they show a low initial strength. However, after prolonged age, the strength increases, while silica fume from the early age itself shows higher strength. In drying shrinkage and creep, we saw fly ash and slag lowers the shrinkage risk, while silica fume increases the shrinkage risk, mainly due to autogeneous shrinkage. And all these three minerals, they mineral admixture, they reduce creep due to densified microstructure of concrete. Finally, we talked in terms of durability. Due to pore densification, we saw Fly ash, slag, and silica film will all reduce the rate of chloride diffusion after prolonged hydration ages. But due to CH consumption in the formation of CSH, SCMs, they increase the carbonation depth as less calcium hydroxide is available for reacting with CO2. Okay, so this is what we talked in the last session, mainly on the part of mineral admixtures. Now, there was one question from last session which someone asked, like maybe from one of the week's assignment. So, let us first see that question and then we'll move ahead with the discussion. Okay, so the question was to calculate the specific surface area for the given grading of rounded aggregates. Okay, so this was the question. Uh, did anyone ask any doubt? Okay, no. Okay, so in this question, what we have given the sieve size and we have given the cumulative passing by mass of the rounded aggregate. Okay, so for calculating specific surface area, the first step will be to calculate the percentage passing. Okay, now what is this percentage passing we are calculating? It means that how many aggregate will pass to one sieve and retain on the next sieve. Suppose how many aggregate is passing through 10 sieve and retaining on 4.75 sieve. These value that you are seeing here, these are cumulative passing. Like 100% aggregates are passing through 20 75 are passing through 10 It is not like 75 is passing through 10 and retaining on 4.75. We want the percentage which is passing through one sieve and retaining on others another sieve. Okay, so that calculation we will do in this column right now. Okay, so how to do that? We go from bottom to up. Okay, so here we have one. So this one is percentage of aggregate passing through 0.515 sieve and retaining on, suppose we can say pan, or 0.075 sieve or 75 micron. Okay, now for calculating the percentage of aggregate passing through uh, zero point 0.3 sieve and retaining on 1.15, like 300 micron sieve and retaining on 150 micron sieve, what we need to do? Total is 10% of aggregate is passing through 300 micron, out of which one is passing through 150. So in between the aggregates that will be there is 9, 10 minus 1. Okay, similarly, percentage aggregate passing through 600 micron and retaining on 300 micron will be nothing but 25 minus 10. So it will be 15. Then we have 30 minus 25. That will be 5. 35 minus 30, that will be 5. 40 minus 35, that will be 5. 75 minus 40, that will be 35. And 100 minus 75, that will be 25. So here 25 means 25% aggregate is passing through 20 micron sieve and retaining on 10 sieve. 20 sieve, 25% aggregate, 25% aggregate is passing to 20 sieve and retaining on 10 sieve. Okay, so now we have aggregates in each size grade. Okay, after this we need to give a sieve size designation to each of these things. Okay, so we need to denote, first we need to find the sieve size range. So in what range this particle is, and then we'll see the further calculation. So this 25%, it means aggregate are in between 10 and 20. Second will be aggregates are in between 4.75 and 10 then 5% are between 2.36 and 4.75 This is 1.18 and 2.36 Okay. Then we have zero point 0.6 and 1.18 5% aggregates are in between this range. Then we have zero point 0.3 and zero point 0.6 0.15 and zero point 0.3 And for the lowest sieve size, we generally use 0.075 and 0.15 Okay, so these are the sieve ranges. Okay, so 25% aggregate is in between this size, 35 is in between this size, 5 is in this range size, 5 is again in this range, and so on. Okay, now for calculating specific surface area, we need to give a designation of to these sieve ranges. So generally for the smallest range, we denote it as P naught. Okay, then this is P1, this is P2, this is P3, this is P4, this is P5, P6, and P7. So this is the general designation we give. So smallest size range we generally denote by P naught, and then we subsequently increase the designation. Okay, so now to calculate specific surface area, which formula we'll use? So we'll have 565.7 times P naught plus P1 by 2 plus P2 by 4 plus P3 by 8 and so on. So this is the formula that we have seen in the uh, previous sessions. Okay, so this is the value that we get for P naught. Okay, so we use geometric mean and we calculate the specific surface area. So using that we get 565.7, and subsequently as we will increase the size range, the value will be divided by 2 because these sieve ranges are in the geometric progression. Okay, so we know P naught, P1, P2, we all know these are the values. Okay, so the answer solution will be nothing but just substituting the values. So it will be 565.7 times 1 plus 9 by 2 plus 15 by 4 plus 5 by 8 plus 5 by 16 plus 5 divided by 32 plus 35 divided by 64 plus 25 divided by 128. Okay, so this is how we will calculate the specific surface area, or we can say surface modulus. So this value will come out to be 565.7 times 11.086, which will be equal to 6271.35, okay, per centimeter. Okay, so this is how we do the calculation. Any doubt in this solution? Anyone has any doubt in the solution how to do the calculation? So this two things we were given in the question, and these things we calculated. Okay, so first we calculated the percentage passing, then we denoted the sieve size range, and then we give this designation to each sieve size, and we use the simple formula. Okay. So I guess if anyone was not able to get this answer of if you are getting the same value and it is not matching what is given in the assignment, then they may have reported a wrong value as the correct answer. So you can just drop them a mail and ask them for the solution, like why the value is not matching. It should come like it should be this value only. So they might have mistakenly reported a wrong value, and you can ask them for the correction. Okay, so now let's move ahead. Now in week 5 we started with the mixture design of concrete. So we know concrete is a heterogeneous mixture comprising of binding material, water, fine and coarse aggregate, and admixtures, which are optional entity. Till date, we have talked about each of these components separately, but now it is the time to see them as a mixture in concrete. Now, what is concrete mixture design? So, it is basically a process of determining proportions of various components that needs to be combined to create a concrete mix with a desired property. Okay, here there is a term that is used which is desired property. So, what do we mean by desired property? So there can be different factors that determine desired property, like strength, workability, durability, appearance of concrete, and use of specific materials in concrete. All of them will dictate the property we need from concrete, and thus it will control the mixture design of concrete. Like suppose for a M30 grade concrete and for a M50 grade concrete, my mixture design will be different. Likewise, for getting a 50 slump and a 150 slump, my mixture design will be different. Another example can be for concrete comprising of just ordinary Portland cement, and for a concrete made with a OPC plus fly ash or silica fume, my mixture design will be different. So several factors or several desired properties can govern the mixture design of concrete. Now, why mixture design is important? Okay, so that uh, to create a concrete which is cost effective, easy to place, compact, and that meets all performance required for the intended use. You can see this again from the same set of example that we have just talked about right now: M30 grade, M50 grade, high slump, low slump. So for a desired property that we want, a mixture design help us to optimize our concrete mix for achieving that intended property in a cost effective manner. Is there some doubt? Answer range given is 1600. So, you can ask them for the correction. Last in the last session also this happened. Na? Just ask them for the correction.
Okay, sir.
Okay, so this is why mixture design is important. Okay, now there are vast number of components that are involved in a concrete mixture design. Some of them are cement grade, so it can be OPC 33 grade, it can be 43 grade, it can be 53 grade. Then we have aggregate size and shape. Okay, it can be rounded aggregate or angular aggregate. It can be 10 passing or 20 passing aggregate. Aggregate grading zone. So for fine aggregates, it can belong to zone 1, zone 2, zone 3, or zone 4. So in this way also my component can vary. Specific gravity of each constituent material used in concreting, like for OPC, specific gravity is important for aggregates or even fine aggregates, or even if sometimes fly ash is used or any chemical admixture is used for, so those values of specific gravity can is also important. It's also a component in my concrete mixture design. Water absorption of aggregate is important because it will help me to keep W by C ratio same as what I desired, and it will help me to take that extra water that aggregate is absorbing into account. Type and amount of admixture added to concrete, like maybe we are adding a super plasticizer or a retarder or an accelerator, they will contribute to the concrete mixture design. Slump value is important, like how much slump I want from my in fresh state, 50 mm, 100 mm, 150 mm. And finally, water to cement ratio. It is the most important factor, we can say, because it plays an important role in governing the strength and the durability of concrete. So these are some of the factors. Okay, and all these factors are needed to be fine tuned and designed to contribute to the ultimate product, which is concrete, for achieving a specific performance demand. Now, the choice and proportioning of these different components in the concrete mixture design is based on achieving a desired performance of concrete. And this desired performance of concrete can be determined in terms of different state. Like in fresh, for fresh state property, the fresh state property, which refers to the workability and handling property of concrete before it sets or hardens. So this is dependent upon the water to cement ratio, grading of aggregates, and shape of aggregate, and it is expressed in terms of slump value. Then we have hardened state properties, which is which defines the performance of concrete in the when the concrete is set and it has gained strength, and this is expressed using compressive strength. We have durability property, which refers to the ability of concrete to resist environmental and chemical attack over time, and this is expressed using applying control on design parameters like water and cement content. So achieving a desired property of concrete we can define in different ways, okay, based on our need. Okay, and these three are most commonly used states where we for which we design the proportioning of our components. Okay, Each of these state, they depend upon the components, okay, in one way or another. Okay, so a particular component, it can influence several properties. Like fresh state is generally influenced by the water to water content, grading of aggregate, and shape of aggregate. My hardened state properties of concrete can be influenced by binder content, binder composition, water to cement ratio, while my durability properties of concrete can be influenced by the water to binder ratio and binder content. Okay, now, to make a concrete mixture using different individual components, there can be different approaches. Okay, so for achieving a desired property and batching different concrete components to achieve those desired property, there can be different approaches a person can opt for. Like one may go for proportioning just by a trial mix. Okay, so there is a correction here. Okay, so for just using a trial mix, one can do the proportioning. For example, suppose a contractor wants to design a M30 grade concrete. So in trial mix, he will choose some cement, some water and aggregate ratio. He will prepare a concrete and he will test for after 28 days to check the strength of concrete. If the strength passes the M30 grade criteria, then the proportioning that he has selected is okay because he needed a M30 grade concrete. But if it doesn't pass the criteria, then he will change the proportion in a certain way and again check after 28 days, and so on. He will do the repetition until he achieves this concrete grade that he desired. So this is known as trial approach. Second is empirical method, that is based on experience. So as you will prepare more and more concrete mixtures, after some time you will get an idea from your experience, like what proportions to use for achieving a certain grade or fresh property. But this comes out to be accurate only when we are experienced in a mixture design. Third is based on recommendations you from relevant mixture design standards. So there are several standards that have been made to aid us in mixture design. Like there is Indian Standard Code, there's ACI method, there is DOE method, which is based on British standard. So following these instructions and steps that are there in these codes, we can one can design the concrete mixtures accurately. Okay, so these are the three different approaches, either by trial mix or by experience or by using the recommendations given by relevant design standard. Now, in all forms of mixture design, one parameter which holds the center stage in proportioning is it is the characteristic compressive strength and target mean strength. Okay, so first of all, you can see a graph here. Okay, where x-axis represents the compressive strength and y-axis is the frequency, that is like number of times a certain strength value was recorded. So when a mixture design is done, different concrete assemblies are prepared, like we have cubes, we have cylinders. Now not all assembly will have the exact same strength. In some there may be, like suppose you have casted cubes. Okay, you have casted 100 cubes. Okay, so in some cubes may be more paste, or in some there is less paste, more aggregate. Their void percent can vary from one cube to another cube, and they can differ in from each other in terms of even if the properties are the same, they can still differ in from one another in terms of some properties. Okay, so suppose like you have prepared 100 cubes. Now when we do a compressive strength testing of these 100 cube, we'll get a curve like this. Okay, so this bell shaped curve. Okay, so this shows that not all 100 cubes are having the same value. Their values are distributed like this curve. Okay, so such distribution of strength that we get is it is known as a normal distribution. Okay, so here we can see there is a higher proportion of value getting near the mean value. Okay, so this is representing the mean, so average of 100 tests that we have done. So more proportions are near the mean value, and the proportions are continuously decreasing as we move away from the mean value. Okay, now how to calculate mean value? It is just by simply uh, uh, summing up all the strength value divided by the number of observation, and the deviation of values that is recorded from mean is known as standard deviation, which is calculated by this formula like you can see here. Okay, so this is the formula for mean value. So suppose we have tested 100 cubes, so you can just calculate the sum of compressive strength of 100 cube divided by 100, so that will give us the mean value. And standard deviation we can calculate by this formula. So individual compressive strength minus mean strength whole square, summation of these value divided by n minus 1. So in our case it is 100 minus 1. So this will give us the standard deviation, how much deviation it is there from the mean. Okay, now whenever we represent concrete, we say M30, M40, M50 like this. So here this 30, 40, 50, it is known as the characteristic compressive strength in MPa megapascal at 20 days of hydration. That is okay. So this characteristic compressive strength at 20 days of hydration is the strength value below which no more than 5% of my sample will die. So suppose you have tested strength for 100 cubes for a M30 grade concrete. Okay, you prepared a M30 grade concrete, 100 cubes you prepared for M30 grade, and you did a compressive strength testing. Okay, so 95 cubes will have a strength equal to or more than 30 mp. Okay, if this is happening, then only we can say the mixture design that we have done, it belongs to M30 grade. Okay, so this is how like my target mean strength and characteristic compressive strength are related. Okay, so target mean strength is something here and characteristic compressive strength is something here. So this is 5%. Okay, and this is 50% because I am at the mean. Okay, so my target mean strength is nothing but characteristic compressive strength, this value plus 1.65 times standard deviation. Okay, this factor 1.65 times s you can see in the graph also, which represents the gap between these two lines. Okay, so whenever we design, we talk about target mean strength and we represent generally in terms of characteristic compressive strength. So we report like M30 grade, M40 grade, M50 grade, but during designing, we are concerned with this target mean strength. So knowing this, we calculate the target mean strength first and then we do the design. Okay, so this is what is about target mean strength and characteristic compressive strength of concrete and how they play a role in the mixture design. Now, try to answer these few questions based on just the basics of mixture design. In the meantime, if anyone has any doubt related to whatever we have discussed till now, they can ask. No doubts yet, no? So just try to answer these questions. For first question, answer is yes. Answer is B. Okay. So all these factors can affect the compressive strength. Okay, which of the following is the most critical, that has been asked. So aggregate gradation will also influence, type of cement will also influence, admixture dosage will also influence, but the most critical factor is the water to cement ratio, and that we'll see when we'll talk about mixture design further in this session, like how the with when we know the target strength, we first go at the water to cement ratio estimation. Okay, so this is the most critical factor among all. So there is a like inverse relationship also. So if I represent my compressive strength on y-axis and water to cement ratio on x-axis, so there is this inverse relationship between water to cement ratio and compressive strength. So as I will increase the water to cement ratio, my compressive strength will decrease, because my porosity in concrete will increase as I will increase the water to cement ratio. And with the increase in porosity, my strength of concrete will decrease. Okay, try to answer the second and the third question now. Second you are saying as D, and for third I am getting a mixed response. For second also I am getting mixed response, C and D. I will wait for like 1 more minute, let others also think, and then we'll see the answer. So for third I got all the options as the answer right now. Okay, we'll see. Okay, so for second question, what second question says, which of the following is not considered while determining the target mean strength? Okay, so the answer will be C. Okay, for target mean strength calculation, as we just saw, we require the characteristics and we require the standard deviation and we require degree of quality control. Like degree of quality control is also required, because if my quality control is low, I will have a higher standard deviation. If my quality control is high, I will have a lower standard deviation. So this indirectly contributes. However, since but we can see there is no condition of curing temperature fluctuation or anything. Okay, that is something which doesn't directly like contribute to the target mean strength, or that it is something we don't consider while determining the target mean strength. Okay, for third question, which of the following changes in the mixture design is likely to increase the bleeding in fresh concrete? So the answer will be D for this. Why? Because higher slump means more flowable concrete, for which we may use a super plasticizer. And if the dosage that of super plasticizer that we have used, it is more than the required dosage, then bleeding can occur. Okay, so this is most likely to increase bleeding in concrete. If I will reduce water to cement ratio, it won't lead to bleeding. Increasing sand content also won't lead to bleeding. Using well graded aggregates, it will make my concrete like more compact. It will make more paste available for workability, but generally bleeding is due to the higher slump mix. In higher slump mix, due to improper dosage of SP that we use, that leads to bleeding. Third question is clear to everyone?
Hello, sir.
Yes.
Sir, actually, we are using a different kind of concrete, like self-compacting concrete is a one kind of concrete,
Hmm.
so which is required a higher slump value, right, sir?
Yes.
So in that case, then there will be no problem for the bleeding.
So that's why I say na, when we talk about high slump mixtures like that we use in self-compacted concrete, we use super plasticizer. Okay, but there also up till a limit only we can use a super plasticizer. Okay, if we go beyond that limit, what we will see, there is bleeding occurring, there is segregation, and all those effects come into action. So that's why generally when we talk about a high slump mix, there are high chances of bleeding to occur. Okay, because if you your super plasticizer dosage becomes important there. Okay. Yeah.
Okay, sir. Sir, higher slump in the sense, what will be the range maximum expected
Higher
range?
slumps means like over 150 mm, you can say collapsible mixtures.
Okay.
Okay, now try to answer these three more questions. Okay, they are all related to like basic understanding of mixture design. Okay, so after this you will be able to like understand the IS codes properly, or you will understand what is required from mixture design. Okay, these are basic questions, so just try answer them quickly. Okay, so for fourth question, I am getting answer as B from everyone. Okay, that is the correct answer. Why is a lower water to cement ratio preferred in high strength concrete? Because if I will have a lower W by C ratio, it will lower the amount of water filled voids in concrete. So this will reduce the shrinkage issues and porosity, or we can say permeability of concrete. And since porosity or permeability and shrinkage issues are reduced, I will get a higher strength value. For fifth question, I'm getting answer as C and or D. Okay. So what is the question? Which of the following is not commonly used method for adjusting workability in a concrete mix? So our correct answer is C. Okay. Increasing the cement content. So increasing cement content, it may reduce, suppose if I have fixed water content and I'm increasing the cement content, so what will happen? My water to cement ratio will decrease, and if my water to cement ratio decreases, it won't improve my workability. So this is not a common method that we use for adjusting workability, or here we can use a term improving workability. Okay, not adjusting. The more proper term will be for improving workability. 6th, for 6th, I'm getting response like D or A or B also. Okay, let's see the question. For a given concrete mix, which condition would likely require an increase in air entraining admixture dosage? Okay, so the correct answer for this will be B. Okay. Why? Because air entraining admixtures, they help to improve the workability, durability, and resistance to freeze thaw cycles in concrete, like of what we have talked earlier also. Now, if I will have a higher fineness modulus of sand, this will reduce the air content in my concrete mix, and it will require an increase in air entraining admixture dosage to maintain the desired air void structure in my concrete. Okay, so higher fineness modulus of sand, it will increase my air voids inside the concrete, and in turn it will increase my demand for air entering admixture in some cold weather concreting conditions. Okay, so that's why the answer will be B. Okay. Okay, so let's move ahead now. So now we will start with the discussion of mixture design as per Indian standard. Now here, though I will be covering the standards, it is more important for everyone to read the standards on their own also at once, like by line reading the standards, because that is the best way to learn a codal provision. Okay, so and these standards like IS 456, IS 10262, they are freely available for download. So you can easily download it from Google and have a reading. Okay. Now, for mixture design, there are two important Indian standards. First is IS 456 and second is IS 10262. Okay. So IS 456 that is Indian standard for plain and reinforced concrete. It provides guidelines for concrete mixture proportioning to achieve desired strength, durability, and workability. And mixture design is typically performed as per IS 10262, which provides a detailed procedure. My IS 456 will just give me basic general principles and requirement. Okay, so there are just principles and requirements that are mentioned in IS 456, but the actual mixture design procedure, it is there in IS 10262. Okay. There are several key points in IS 456 that are related to mixture design. Like, first, we have the type of concrete mixture. So, as per Indian standard, concrete mixture is broadly classified into two types. There is nominal concrete mix and there is design mix concrete. Okay, nominal mix concrete and design mix concrete. Nominal mixed concrete includes specified proportions of mixture components for low strength concrete like M10 grade, M15 grade, and M20 grade. While design mixed concrete uh, is where we engineer the proportion of individual component through laboratory trials for achieving a particular strength and durability requirement. And this is done for M25 grades and above. Okay, so for nominal mix, we have desired specific proportion like sand to cement to, like aggregate to cement to sand ratio. So these proportions are specified, it is fixed. We don't model this proportion for low strength concrete. However, for design strength mixed concrete, we engineer this proportion based on trials for strength and durability to get a certain strength grade. Okay. In IS 456, table 2, we can see this division. So in table 2, concrete is divided into three groups. We have ordinary concrete that is that is prepared by nominal mixed design, and then we have standard concrete that goes from M25 grade to M55 grade, and we have high strength concrete. Okay, so ordinary concrete has grade from M10 to M20. Standard concrete has grade from M25 to M55, and high strength concrete has grade from M60 to M80. So if we read the points below, first point says that here 15, 25, 30 all are the values that refers to a compressive strength of 150 mm size cube at 20 days of hydration. So these all values that are determined here, they are determined by from compressive strength of 150 side cubes at 28 days. Okay, and the second point says for high strength concrete that is greater than M55, the proportioning shall be done from based on past literatures, like from people who have previously done the proportioning and published an article. So using those previous literatures and experimental trials, we generally design for high strength concrete. Okay, so IS code that we use mainly for the standard concrete. Okay, ordinary concrete we already have the mixed nominal proportion, so we don't do any engineering in this thing. The designing part that we do is for the standard concrete, and for high strength concrete we generally go by trial approaches, or by based on experience we calculate the proportion for this. Now, for nominal mix design, we have table 9 that is there in IS code. Okay, that is titled as proportions of nominal mix concrete. Here, for specific low grade concrete, quantity of total aggregate per kg, 50 kg of cement, the ratio of proportion of fine aggregate and coarse aggregate, and the quantity of water is mentioned. Okay, so just following these proportion we can prepare a low strength gate. Okay, so suppose I want to prepare a M10 concrete. So what this code says, what this table take says, that I need to take 480 kg of aggregate per 50 kg of cement. Okay, in aggregate I need to keep a proportion of fine to coarse aggregate generally 1.1 is to 2. or it can be 1 is to 1 1.5 or 1 is to 2.5. In this range I need to keep the proportion of fine and coarse aggregate, and I need to use a water or 34 liters of water per 50 kg of cement. So if these proportions I will take, I may get a strength of M10 grade. Okay, so like this we can use this code to these predetermined mixes we can use to get a nominal low grade concrete strength without requiring any trials or any engineering. Okay, however, if we see in reality nowadays, a concrete strength below M25 grade is rarely used. So this table you won't find to be of much use in practice, but it is just there for reference. The second key point of IS 456 is mixture proportioning, which is primarily influenced by four key parameters. First is the water to cement ratio, which should be kept as low as possible for strength and durability, and maximum water to cement ratio for different exposure conditions is also specified. Then we have cement content. So minimum cement content is specified for different environmental conditions in IS 456. Aggregate selection of fine and coarse aggregate is based on grading, shape, and strength. And admixtures like fly ash, JGBFS, plasticizers, and retardants can be used for improving the workability and performance. So these are the key mixture proportions that IS 456 identifies in a mixture design. Third point is the target mean strength. So whatever concrete we prepare, it is for achieving a certain target mean strength when we know the characteristic compressive strength that we require. So simply saying, we know the FCK value and we want to design for a target mean strength value. And this we do by calculating the target mean strength using this formula that we have already seen. Okay. Fourth point is workability. So workability depends upon the placement method, reinforcements, arrangement, and environmental condition. And this workability that we require, it is measured in terms of slump test, compaction factor, and VB test. So these three testing methods are recognized by IS code for determining the workability. And the fifth and the most important point from IS 456 is the durability requirement. Okay, so IS 456 specifies limits on concrete grade, W by C ratio, and minimum cement contents based on exposure condition. So exposure condition can be mild, moderate, severe, very severe, and extreme. So as you can see here in table 3, which is titled as environmental exposure condition, this is used to set a classification of exposure environment based on the condition. Like we say, exposure is mild when concrete surface is protected against weather and aggressive condition except those situated in coastal areas. So when this is the exposure environment, we say that the environment is mild. Similarly, like for severe, we say concrete surface is exposed to severe rain, alternate wetting and drying, and occasional freezing. So if my concrete is exposed to such condition, we say that the condition is severe. And like in extreme, we say concrete is in contact with buried is in contact with or buried under aggressive soil or groundwater condition. It is in tidal zone, or it is in direct contact with liquid solid aggressive chemicals. So if my concrete is under such threats, we say that the environment is extreme. So based on this table, based on the location of my concrete, I can determine the environmental severity before designing the concrete. Okay, so I know in which location I am preparing my reinforced concrete, like where is my application of reinforced concrete, and based on that location, I can first characterize that location in different terminologies like mild, moderate, severe, very severe, or extreme. Okay, and this environmental like classification is done so that we can have a suitable resistance to sulfate attack, corrosion, and freeze thawing cycle. There is one more table in IS code which I will just expand so that everyone can clearly see. So this is table 4, okay, which specifies requirement for concrete exposed to sulfate attack. So in this table, based on the amount of sulfate that is present in soil or groundwater, the type of cement to be used, the minimum cement content, and the maximum water to cement ratio limits are specified. Okay, so when we do the designing, suppose we have calculated certain water to cement ratio or certain cement content, we need to go back and check at these values also, and the value whatever we have determined, they should satisfy these things before moving ahead. And then this is the most important table for durability consideration, that is table 5, titled as minimum cement content, maximum water to cement ratio, and minimum grade of concrete for different exposures with normal weight aggregate of 20 nominal maximum size. Okay, so here, based on the exposure conditions that we have already arrived at using table 3, we uh, there is different limits that have been set on water to cement ratio, cement content, and concrete grade for both plain concrete and reinforced concrete. Okay, so for example, suppose I am talking about constructing a residential building near shoreline. Okay, where my concrete will be exposed to seawater spray. Okay, now since seawater is rich in chloride, so as per table 3, my structure will come in exposure class which is very severe. Okay, and for very severe exposure and for a reinforced concrete, I have these limits that has been specified by IS 456. Okay, so my minimum cement should be 340 kg per meter cube, maximum water to cement ratio should be 0.45, and minimum grade of concrete that I need to prepare is M35 grade. Okay, so based on this, whatever value we are getting, we need to cross verify with this range so that before moving into the actual mixing of proportions. Okay, so this is how during concrete proportioning we use IS 456 to set the limits on different design parameters. Now, after IS 456, we have IS 10262. So, according to IS 10262, steps of concrete mixture design is as follows. Okay, so first step is determining the target mean strength of a mixture proportion. So the in order that no more than a specified proportion of test result are likely to fall below characteristic strength, the concrete mixture has to be proportion for higher target mean strength target mean compressive strength. Okay, so we design concrete for a target mean strength. Okay, and we know this FCK value. Okay, now, total number of test sample that is required to calculate the standard deviation, it should not be less than 30 sample. However, when sufficient test results are not available with us to calculate the standard deviation, we have table 1 in IS 210262, from where we can take the assume the value of standard deviation. So suppose you are on a site, you want to prepare a M30 grade concrete. Okay, now for M30 grade, you need standard deviation S value also, but you don't have enough sample to obtain this S value. So what IS 10262 says, if you don't have enough samples to calculate S value, use this table 1 to assume the S value. So for M30 grade, we can assume a S value of 5 Newton per mm square. So standard deviation, we can assume this, and we can calculate the target mean strength for our designing. Second step is selection of water to cement ratio. Okay, so selection of water to cement ratio is generally based on experience. Okay, that is based on established relation, or for starting trials, we can use the deliberity criteria also from table 5 for IS 456. So there is no general like curve that is given in IS 10262 for relating water to cementation strength. They say that either go with experience or use starting value you can use as the limit that is there in the durability criteria. Like here you have mentioned there are different limits mentioned, right? So you can go with these limits instead of, if you don't have experience or you don't want to do any trial thing. Okay, now this chart says that W5C ratio is the only factor which is influencing the compressor strength. However, just relying on W by C ratio to get a strength may not be enough. Okay, and that's why in trial mixture design is done first. Okay, so whenever we are doing a mixture design, we get a trial mix. Okay, we don't say it as the final mix, it is my trial mix. Okay, so first we do the trial mix, so that we can be sure that whatever proportions we have take, it is able to reach the required strength value. And if it is not able to reach the required strength value, we'll do the necessary adjustment in the proportion before actually taking that mixture design on field. Okay, so whatever mixture design we are talking about, it is a trial mixture design. Now, after this, the third step is selection of water content. So, water content can be influenced by several factors like a increase in aggregate size, reduction in W water to cement ratio, or slump, or maybe use of rounded aggregates or water reducing admixture. They all will reduce the water demand. While increased temperature, cement content, slump, water to cement ratio, aggregate angularity, and decrease in proportion of coarse aggregate, they will increase the water demand. So table 2 is there in IS 10262, which gives us the value of maximum water content per meter cube of concrete based on the nominal aggregate size. Like we can see, we have a nominal aggregate size of 10. So we need to have a water minimum water content, maximum water content as 208 kg. Okay. And these values that are mentioned in this table, these are for angular coarse aggregate and for 25 to 50 slump range. However, if we want to make adjustment for other coarse aggregates or other slump ranges, there is clause 9.2 that is mentioned in IS 456 where corrections are mentioned. Okay. So this correction you can see in this table that is listed for each 50 increase in slump, the water content needs to be increased by 3%. For subangular gravel plus crushed and rounded aggregates, these are the adjustments that we need to do in the water content. And when we are using a super plasticizer or an high range water reducing admixture or a normal plasticizer, this is the range in which we need to decrease the water content, either by 5 to 10% or by 10 to 30%. Now, fourth step of mixture design is calculation of cementitious content. So my cementitious content includes both my ordinary Portland cement and supplementary cementitious material. Okay, that we will calculate. Now we know the W by C ratio and we know the water content. So if we know these two things, we can calculate the cement content. Okay, and this cement content that we have calculated, it needs to be checked with the minimum cement content requirement as per durability criteria, which is there in IS 456. Okay, so we need to check for the criteria in IS 456 just to verify whatever cement we are obtained is it is in the required limits. Okay, then we have step 5, which is calculation of total aggregate content. So we know cement, we know water, and we know if we assume 1 meter cube of concrete, so my volume of aggregate will be nothing but 1 minus volume of cement and volume of water. And for calculating volume of cement, we'll divide mass by the specific gravity times 1000. So 1000 is my density of water, and I will divide subtract mass upon mass of water by 1000 to get the volume of water. And this will be my volume of binder. So cement, supplementary cementation material, all will include this. So if I will subtract volume of binder and volume of water, I will get whatever remaining volume, it is the volume of aggregates. After this, we have proportioning of aggregate. Like in aggregates, how much there is coarse aggregate and how much is fine aggregate. Okay, so this is done using table 3. Okay, so in table 3, you can see for different nominal maximum size of aggregate and different zone of fine aggregate, there are different values which are mentioned. Okay, so suppose I have a nominal maximum aggregate size is 20 and my fine aggregate is in zone 2. So code says 0.62 is the ratio. So of total aggregates A, my 0.62 fraction should be coarse aggregate and the remaining fraction should be fine aggregate. Okay. Now, for more workable concrete, which is sometimes required during placement, if we are doing placement by pumps or when concrete requires to be remain workable for a long time or in reinforced section, we may we may reduce this coarse aggregate fraction by 10% also. That is what code says, that you can do an adjustment of 10% if you want a more workable mix. Once we get the coarse aggregate content, we can estimate the fine aggregate content. So it will be nothing but 1 minus factor from table 3. So this factor, suppose 0.62 is my coarse aggregate. So my 0.38 of total aggregates will be fine aggregate. So we know the volume of fine aggregate, so we can estimate the mass of fine aggregate. Now we know the mass of fine aggregate and we know the mass of coarse aggregate also. But sometimes in coarse aggregate we may use different size combinations. Like generally it is not like we are only using 10 mm passing aggregates, or we are just using 20 mm. We may go for both mixture of 10 and 20 mm aggregate. Okay, so if we want to go for such mixes, which is generally used, we refer to IS 383. Okay, so based on IS 383, this table that we have already seen, so whatever aggregates we have, we will determine the sieve designation of those aggregate. And suppose we are taking 50-50% of both of these aggregate, and we wanted 20 mm nominal mix size, so we'll check whether 50-50 proportion will give me this 20 mm mix or not. If it is giving me this range, then we can go for 50-50% of both aggregate. Okay, so in this way we can use different coarse aggregate fractions. And finally, the most important step is the proportioning. After proportioning, the most important step is the correction of water content based on moisture content in aggregate. Okay, so when we do the mixture design, we assume that we have saturated surface dry conditions of aggregate. So like you can see in this mixture, in this photo, there can be different types of aggregate. It can be oven dry, it can have some moisture inside, it can be completely saturated by moisture, or it can be oversaturated by moisture. Generally when we talk about mixture design, we assume that my aggregate are in this state. However, in reality my aggregates are generally not in this state. They will be either in this state or in this state. Okay, so we need to have certain amount of additional water that we should take, so that we can make aggregates achieve this state. Okay, and that will also account for certain correction in aggregate content also. Okay, so ssd weight means when my aggregate is completely saturated by water from inside but my surface is dry. Okay, now suppose I know the water absorption capacity of my dry aggregate. Okay, so this, from this to this, I know how much water is required. And I know, like suppose in conditions of aggregates that I have is in this state, so I know how much moisture is there in aggregate. Okay, so either my aggregates can be dry, either my aggregates can be ssd, or my aggregates are in between dry and ssd. So suppose my aggregates are in between dry and ssd, so it has some moisture content which is lower than the water absorption capacity. So that moisture content I also know. Okay, so if I know these two value, what I will do, I will first calculate the dry weight of aggregate. So dry weight of aggregate will be nothing but ssd weight that we have determined using mixture design into 1 minus the water percent, because in ssd weight of aggregate, w percent weight is due to water. So if I will subtract that w percent weight, I will get the dry weight of aggregate. Okay, and now once I reach the dry weight of aggregate, to achieve the weight of aggregate of that in place aggregate which is in between dry and ssd, I will just add the moisture content. So adding the moisture content will give me the in situ aggregate weight. So this is how I do the correction for aggregate weight. Now, for water content correction, total absorbed water by dry aggregate will be nothing but dry weight into water absorption capacity and total additional water that I need to add. Suppose from mixture design, I determined water W. Okay, so either I will need to the amount of water that I need to add in this W, which will be absorbed by aggregate. It will be nothing but total water absorbed by aggregates when they are in dry state, minus what is actual moisture content in my aggregate. Okay, so using this equation I can calculate the additional moisture that my aggregates will absorb. So my aggregates are in this state. Now to reach from this to this, how much additional water I need to supply, that I can calculate using this formula. Okay, that we have already we have also seen as how it is derived. So this is the final part, that is known as correction of water content based on moisture content of aggregate. So this chart that was shown in NPTEL recording, it just summarizes whatever we have discussed right now in IS the in mixture design. So assuming that you have all gone through this, I will just skip this part and move to the question so that you can now see how to do the numericals. Okay. So first try to answer these three questions, like based on what, just to check whether you have understand IS design properly or not. Just try to answer these three questions based on the IS mixture design, and then we'll see a numerical question. Okay, quickly answer this question. And in the meantime, you can ask any query if you have in the design part that we have discussed. Okay, I have some questions here. In IS code, there is no recommendation for grade which is above M40, and how we calculate W by C ratio for M55. I didn't got your question, like what you are trying to say. That 1000 division is because we know this specific gravity of cement or aggregate. We know, we want to know the density. So what is specific gravity? It is nothing but density of my material upon density of water. So density of material will be nothing but specific gravity times my density of water, which is 1000 we can take. Okay, so volume is mass upon density, not mass upon specific gravity. So that's why I have multiplied by 1000 or divided by 1000 in the calculations. Every increase or decrease of 25 mm slum, 3% water needs to be considered. So the proportion that has been mentioned here. Okay, these water content is for 25 to 50 mm slum. If I want more slum, then I need to increase my water by 3%. So suppose I want 100 mm slum. So whatever volume of water I am taking here, it will be nothing but 208 into 1 plus 0.03. So 1.03 times 208 water I need to take if I want a 100 mm slum. What is the nominal aggregate and graded aggregate? How we decide the graded aggregate? Graded aggregate means when you're you are taking two different proportions of aggregate and mixing them together. Okay, suppose I have 10 passing aggregate and I have 20 passing aggregate. Now whatever design I am doing, it is I am doing for a nominal maximum aggregate size of 20 Okay, so if suppose I take 50% of 10 and 50% of 20 am I getting a nominal aggregate size which is defining this value? Okay, so that is what we have discussed here. Okay.
ఇలా టూ ఉంటే ఇలా టూ
uh,
ఇలా సిక్స్ ఇలా సెవెన్ ఉంటే ఇలా సెవెన్
I will mute you for some time. Okay. In IS 456, W by C ratio for M40 is considered what when I try to design a mix. What will be the W? See, what W water to cement ratio we should choose, it comes from experience or from trial mix. There is nothing that is mentioned in either IS 456 or IS 1026 that directly says like, suppose for M30 you need to take W by C ratio as 0.3, for M40 you take 0.25. There is nothing like that mentioned. W by C ratio choice comes from experience or either considering the minimum durability requirement. Okay, so using that we take a W by C ratio and we do a design, and that is why the design is known as a trial mix. It is not my final mix. Right now, suppose for M40 grade, you have taken a W by C ratio of zero point 0.4. You will do complete designing, assuming that your W by C ratio is zero point 0.4. You will prepare your concrete and you will do the strength calculation at 20 days. Now you will check whether the strength that you are getting, it is passing M40 or not. If it is passing M40, then the proportion W by C ratio that you choose, it is correct. If it is not passing M40, then you may need to adjust the proportion. So that's why we say it is a trial mix design. So generally, suppose for M40 grade, you choose a W by C ratio of 0.45. Then for M55, when you are doing a trial mix, you can take a W by C ratio of 0.35 or zero point 0.4, anything, because you know as W by C ratio will decrease, my strength will increase. So that is how you can take an initial judgment of what W by C ratio you need to go forward with. But directly we can't fix a specific value. Okay. Try to answer these questions quickly so that we can move ahead. So what will be the answer for the first question? According to IS 456, which of the following statement regarding mixture proportion is true? So the answer will be D. Okay, there is one more question that has come. Is there any consideration for abrasion resistance to which a warehouse concrete floor or a closed building floor is subjected and meets? See, durability property like abrasion resistance and all, you need to calculate separately. Like after you have prepared your concrete, you need to check whether it is passing the abrasion testing or not. Directly, there is nothing mentioned in code like for this abrasion resistance, you need to have this grade or this properties. For durability, abrasion resistance is also part of durability of my concrete. Okay, for durability, code just specifies limit on cement content, water to cement ratio, and grade, and that too based on the exposure environment, mainly for sulfates and chloride attacks. Okay, abrasion, there's nothing mentioned directly while designing. That is something you will prepare your concrete and you will test and you will check whether it is passing your abrasion requirements or not. If it is not passing, you will prepare a higher strength concrete. So suppose M30 is not passing, then you will go to M35 and you will check. Okay, we'll just quickly go through these questions first. So for first question, answer will be B. Okay, so we have talked this already. So mixture design should have lowest possible water to cement ratio without sacrificing workability. So this is what is mentioned in IS 456. Now, second question, question number 8. As per IS 10262, selection of water content in the mixture design is primarily based on. So, the answer will be. Okay, answer will be B. Exposure condition and slump requirement. So exposure condition can define my W by C ratio, which can affect the water content. My slump requirement can also affect the water content. And this also can affect maximum aggregate size and workability. So workability again, it is the same thing for as slump requirement and maximum aggregate size. Like we saw here in this table, my nominal maximum aggregate size can also determine my affect my water content choice. So both B and C will be the correct answer. Third question, for reinforced concrete mix slump requirement as per IS 456 for normal conditions should be in the range. Okay, so for this question, correct answer will be B, 50 to 100 mm. So for reinforced concrete, like in beams and slabs, we require a moderate workability range of 50 to 100 mm. Okay, lower slump like 25 to 50 mm, it is generally used for mass concreting like in foundations. However, higher slump, that is 100 to 150 mm or 150 mm and above, they are usually used when we want a more flowable concrete. Okay, such as where we have a heavily reinforced section or we want to pump concrete, then we require such high slump values. However, for normal conditions in beams and slab, we generally require a slump in this range, 50 to 100 mm. Okay, so now we will see a mixture design problem. Okay, so just read this question for a minute, think how we'll proceed, and then I will give you step by step solution so that you can understand how to use both IS 456 and 10262 for design. So just try to read this question. Let me first solve this doubt. Why strength criteria have no necessity in IS code for mixed design, but ACI code considers both strength and durability? So these are some of the limitations. Like some code have some limitations, some other code will have some other criterias of defining. So like we have strength criteria. It is not like we don't have strength criteria. You see in this table here, you can see minimum grade of concrete. There is strength criteria that is mentioned. Based on exposure severity, you need to have a strength, minimum strength. So suppose your concrete is in severe exposure, your minimum concrete strength should be M30. So there is strength criteria in IS 456 also. So here we are considering both durability and strength. So based on the durability demand, we are keeping a check on the minimum grade of concrete. So there is strength criteria in IS 456 also. Okay, so I'm assuming that everyone has read the question. So what question says, we need to design a concrete mix for M30 grade to be used in reinforced concrete exposed to severe environmental condition, and the structure requires a slump of 100 mm, and we have been given following data. We are using M43 grade cement. Maximum aggregate size is 20 mm. Specific gravity of cement is 3.15. Specific gravity of coarse aggregate is 2.70. For fine aggregate is 2.60. Water absorption of coarse aggregate is 0.5%. Water absorption of fine aggregate is 1%. What moisture content of aggregates are nil. This means my aggregates are in dry state. Okay, if there is no moisture. Sand that I am using, it confers to zone 2 grade. Exposure condition is severe, already mentioned in the first line. Degree of supervision is good. Okay, target slump already mentioned, and standard deviation from site data. So suppose, so it is already given to us that standard deviation is 5. However, from table also, if you would have calculated, it will come out to be 5 MPa. So this point won't affect much. Okay, so these are all everything that we already know for our material and for the demand that we have, and we need to make a trial mix, okay, out of this. This is just for like try design, like just to explain you a mixture design. Right now we are not focusing on why we are using that, why we are using that. Okay, generally we used 43 grade, 53 grade. Why 33 grade cement is outdated? Okay, it is because nowadays we want a higher strength. Okay, whenever we do concreting, because of severity of exposure conditions, we require higher strength. We require a high early strength. Okay, in M33 grade, you will see the strength. We won't be able to achieve the required strength that we want from concrete. That's why generally nowadays M43 and M53 are used. Earlier, the strength demands were lower. We didn't prepared like concrete of M60, M65, M70. That was not there earlier. That's why M33 grade used to work. But nowadays, instead of preparing a M20 concrete, which was common earlier, now commonly casted concrete has been M40, M35 grade, for which 33 grade cement won't be suitable. Okay, that's why it has become outdated. Okay, now just let's see how we will solve this question. Okay, so my step 1 is determining the target mean strength. Okay, for this I will use IS 10262 table 1. Okay, so in table 1 where standard deviation was mentioned, however we don't require that because it is given already in the question, but still we can use that. So target mean strength will be nothing but FCK, which is M30, so 30 plus 1.65 times 5. So this will come out to be 38.25 MPa. So this is my target mean strength. So this is my step 1. So step 2 will be selection of water to cement ratio. Okay, now either we can go by experience, or what we'll do in this question, we'll use the durability limit that are mentioned in table 5 of IS 456. So we know severity condition is severe, so exposure condition is severe, that has been given to us. So as per IS 456, you can see for severe condition, maximum water to cement ratio that we can take is 0.45. So suppose we are taking 0.45 only in this question. Okay, so let's take a water to cement ratio of 0.45. You can also take zero point 0.4 if you want, but right now I'm taking 0.45 because this is satisfying my durability criteria. So it is mentioned maximum 0.45, so you can take zero point 0.4 also, you can take 0.35 also, but right now I've taken 0.45. So step 3 will be determining the water content. So for this we'll use IS 10262 table 2. Okay, so what has been given to me in the question, 20 mm is my nominal aggregate size. Okay, maximum size of aggregate is 20 mm. Okay, target slump is equal to 100 mm. Okay, and I am assuming, since there is not given in the question, I am assuming we have angular aggregates. Okay, so for 50 mm slump and 20 mm MSA, maximum aggregate size, as per table 2, like here you can see, as per table 2, for 50 mm slump and 20 mm nominal aggregate maximum aggregate size, my maximum water content is 186. Okay, so this value will is, we have water content as 186. However, for 100 mm I need to, for 100 mm slump, which is 50 times 50 more than what slump we for what water we determined for 50 mm slump. So we need to increase by 3%. The water content we need to increase by 3%. So my water content will be 186 into 1.03, so it will become 192 kg for getting a 100 mm slump. Now
Sir, sir, 1 second. Sir, actually, water content need to increase by 6%, right, sir? Actually, because every 25 mm slump we need to increase, no?
it is 25. No, for each
Because
increase of
see,
50 mm, it is mentioned that the increase should be 3%.
every 25 mm slump we need to increase the 3 percentage, because now the slump per 50 mm slump it is yes,
What?
as per the IS code it is 25 to 50, it is given the water content that is 186.
Yes.
Okay, so now we have a slump value is 100 mm.
Huh?
So every 25 mm increase of slump, we have to increase the 3% of water.
No, no, you see na what is there in the code.
I think that is why I wanted to I asked because I think it is mentioned wrongly maybe because it is not 50, it is 25 maybe.
Okay, let me check.
Yes, sir.
No, it will be in IS 10262, right?
Maybe
Generally,
correction is there in IS code.
let me check. Maybe I have referred to the earlier code. That's why. Now you see,
Okay,
okay, for every additional, okay. Now the correction has been done. For 50, 25 mm slump, we need to increase 3%. Okay. So this is like for every 25 mm increase. Earlier it was 50 mm. Now it has been changed to 25 mm. Okay. So
yes, correct,
nothing.
sir.
We can do this proportion will change to 6%. Okay. So my value will come out to be 186 times 1.06, so 197.16. Okay, this is a recent update, I guess, that has been done. Okay, so this is the correction that will take for slump. Okay, for 100 m slump we have increased for 6%. Okay, since there is nothing that is been mentioned in the code about SP dosage, we are not using in this question. However, you can try also and repeat the question. Suppose you want to use a plasticizer, you can check, you can adjust the water content. Okay, generally nowadays using SP is very common. Okay, a concrete without the use of a super plasticizer, those are rare. Okay, so you can do that trial on your own. Right now I'm not assuming any super plasticizer taken. Okay, now step 4 will be cement content estimation. Okay, so this will do by IS 456 table 5. So table 5 will give me the limit criteria. I know the W by C ratio and I know the water content. So my cement content will be nothing but 197.16 times 0.45. So this will come out to be uh,
436.
197.16 times 0.45. Oh, sorry, divided by 0.45.
438.
So it will come out to be 438 kg. Okay. Now, what IS 456 code says the minimum cement content that we need to take. So, what is the condition? Let us go back. So, for severe condition, the minimum cement that I need to take is 320 kg, and I am taking 438 kg. So, it is okay. Okay, we can take this value. We can go ahead with this value. Okay. Step 5 is volume of total aggregates. Okay, so volume of total aggregates. Suppose I am assuming I am preparing a 1 meter. I am preparing 1 meter cube concrete. Okay, so my volume of total aggregates will be 1 minus 4. What was my cement content? 438 divided by 1000 into 3.15. So this is specific gravity into density of water. Okay, so this will give me density of my cement, and I know the mass of cement, so mass upon density will give me volume minus my water content, which is 197.16 divided by 1000. So this will come out to be 1 minus 0.438 divided by 3.15. minus 0.19716. So this will come out to be 0.663. So 0.663 meter cube. So in 1 meter cube concrete, my volume of aggregates will be, total aggregates will be 0.663 meter cube. Okay. Now next step. Okay. So step 5 we have completed. Step 6 is proportioning of coarse and fine aggregate. Okay. So what has been given in the question, I have 20 maximum size aggregate and I have zone 2 sand. Okay. So for this two, I can go to the table. I will refer to the table again. So which is the table? So we have table 3. So 20 aggregate and zone 2 sand, we need to take 0.62 as the ratio volume of coarse aggregate out of total aggregate. Okay. So volume of coarse aggregates will be 0.62 times total aggregates. So total aggregate volume is 0.663. So this will come out to be 0.62 times 0.663. So 0.411. So this is the volume of my coarse aggregate, and mass of my coarse aggregate will be, I know the volume. So mass will be volume times density. So 0.411 times density, 2.7 is the specific gravity, and 1000 I will multiply for converting specific gravity into density. So this will come out to be 0.411 into 2.7 into 1000. So 11011 triple 10 we can round off to. So triple 10 kg aggregates I will take per meter cube of concrete. So this is coarse aggregate. Volume of fine aggregates will be 1 minus 0.62, so 0.38 times 0.663. So this will come out to be 0.38 times 0.663. So 0.21, 0.252 we can round off to. So 0.252 meter cube is my volume of fine aggregate, and mass of fine aggregates will be equal to 0.252 times 2.6, that is the specific gravity of fine aggregate, into 1000. So this will come out to be 0.252 into 2.6 into 1000. So it will be 655 kg of fine aggregates per meter cube of concrete. Okay. Now step 7 is mixing coarse aggregates of different sizes. Okay. Now for this we need the sieve analysis results also, which we don't have right now. However, I will just like tell you, like in general practice in India, we take around 50-50 proportions of 10 down and 20 down aggregates. But since it is not mentioned right now in this part, like we don't have the sieve analysis results, so we will skip this part for now. But suppose if you have the sieve analysis results also of 10 down aggregates, 20 down aggregates, so you can take check how you can take like 50% of both. Is it giving you a maximum aggregate size of 20 If it is not giving, you can adjust 45 55, 40 60, or 55 45. That adjustments also you can do, so achieve a maximum aggregate size of this demand. Okay, so right now we are skipping this part since we don't know the sieve analysis result. But generally in practice we take 50% of 10 down aggregates and 50% of 20 down aggregates. Now the last step is water correction. Okay, so we have given that moisture content is 0. So if moisture content is 0, it means my aggregates are in dry state. So we have dry state, so dry state of aggregates. So this means that first we need to correct the aggregate content, because we assume that aggregate are in SSD state when we are designing. So whatever design we have done till now, we have assumed that the aggregate and the SSD state. So first we need to find the corrected aggregate content. So that will be, for course aggregate, it will be, what is my SSD weight of course aggregate? 1110 times water 1 minus my water absorption. So water absorption was given out as 0.5%. So it is 0.005. So this will give me the dry weight of aggregate. So what I am doing, I am removing the weight of water from my total SSD weight of aggregate. So that will give me the weight of my dry aggregates. So it is 1110 times 1 minus 0.005. So it will come out to 1104 kg. So this is my dry weight of coarse aggregate. And similarly for fine aggregate, it is 655 times 1 minus 0.01, since 1% was point 1% was the uh, uh, given value for water absorption in fine aggregates. So this will come out to be 665 into 1 minus 0.01. So it is 658.35. Okay, so this is my fine aggregate. And now for water correction, what we'll do, total water will be nothing but whatever water we have determined, that is 197.16 plus my water that the aggregates will absorb. So whatever water my dry aggregates will absorb. So it is 1104 times the water absorption capacity of my aggregate, that is 0.005, plus 658.35 times 0.01. So this much water my aggregates will absorb. So this much water I need to take additionally, so that my dry aggregates can reach the SSD state. So this will come out to be 197.16 plus 1104 into 0.005 plus 658.35 times 0.01. So this is the corrected water content that I need to take, 209.26. So 209.26 kg. So this is the corrected aggregate weight. So this is how trial mix design is done. So this is my total water content. These are my aggregate contents in dry state. Okay. And initially I have calculated my cement content also. Okay, so I have known now know all the proportions. So based on this proportion, I will do a trial mixture design, and then I will check whether my strength, I am able to get a strength of this value and slump of this value. If I'm able to get the strength and the slump, then my mixture design has passed this criteria, else I will need to adjust the mixture design. Okay, so this is how mixture design is done based on IS code.
Hello, sir.
Yes.
Sir, hello.
Yes.
Sir, after doing a mix design, so we have to go for the trial mix.
Yes.
So for trial mix, how many days we have to wait? Like
20
because
days.
to achieve
20
the
days. 20 days.
20.
Because at 20 days, we'll get the characteristic compressive strength value. And it should satisfy the M30 grade criteria. And for slump, fresh record slump you need to take. So after mixing, you need to take the fresh slump, and it should pass the 100 criteria.
So then it is a critical because every mix design you have to wait for 28 days. Then it is a
That
long
is thing.
process
That's why
to
trial mix
decide the.
design is initially done in laboratory and not on field. So before going on field, you need to do a trial mix so that you can engineer their proportions, and that is why that is done in in laboratories.
Okay, sir. Okay.
Okay, there is one question here. It will be 186 into 1.03 into 1.03. No, directly 186 into 1.06. So for every, like, if for 50% increase it was 3%, for 100% it will be 6% increase. Water content reduces the coarse aggregate weight proportion according to for every zero point 0.5 reduction in what there is one. It depends upon the moisture content of aggregate. Okay, like we can't fix like how much water content we need to reduce or increase. It will depend upon the moisture content and the uh, water absorption capacity of aggregate. So we can't directly say that this much moisture we need to reduce or increase.
So this is in the IS code 10262.
Okay, so
Uh,
where.
Code say if we decide the proportion fraction of the course aggregate,
Hmm.
the code considers the zero point 0.5 bar to cement ratio. At zero point 0.5 bar to cement ratio, we can code can considers that proportions.
What proportions you are saying? You mentioned
Uh,
regarding water content.
as water content
Hmm.
with respect to course aggregate.
Hmm.
Code says at zero point 0.5 bar to cement ratio, uh, code says
You're talking about this line, right? Approximate value of
yes,
aggregate
yes, yes,
volume
yes.
in for a water which may suitably. So this is something you can adjust, but since you don't know what adjustment factor you need to take, you can do a trial mix. Okay, if you want a more workable mix, code says that you can decrease the aggregate content by 10% or and all those things. But there is not like nothing mentioned like what adjustment you need to take. This adjustment that you are talking about, it is for more workable concrete. If you want to pump your concrete, then you can take adjustment of 10%. Okay, but suppose you don't want to pump your concrete, you are making a normal mix. This table is as per zero point 0.5 ratio. So right now initially you can go with whatever proportions you are getting for zero point 0.5 ratio. Then once you have final mix design, you can make an adjustment if you want. If you are not able to get whatever desired property you want, then you can make the adjustment, but it is not directly mentioned that you need to increase or decrease by any amount. You see in this paragraph, there is nothing mentioned directly like how much increase, how much decrease we need to do. Only when you want a more workable concrete mix that is needed for pumping, then only correction is mentioned. You may increase. That also it is written. You may, it may be desirable. It is not completely like you. It is not necessary to do. It can be done. It is that is what is written.
Okay, sir.
Okay. So let's move ahead. So since we have less time left right now, so what I will do, I will just discuss the DOE method. Okay, design of experiment method, how it is done, and this final question we'll take in the next session. So next session we'll first start with this question and then we'll move ahead. So right now, just let's
Sir,
see.
sir, screen not visible.
No, it is visible.
Screen is not visible actually.
Is this problem occurring with everyone?
To me, it is
Screen
not
is
visible. I don't know that.
Can anyone else reply?
Visible,
No,
sir.
sir, no.
No, we can, like, people can see. It may be due to your network fluctuation you are not able to see, because from my end it is stable.
Okay, sir.
Okay, there may be network fluctuation at your end, that's why you are not able to see. Okay. Okay, so let's quickly wrap up the DOE method in 10-15 minutes and then we'll end the session. Okay, or I will wait, like give you extra time for any other query, and that final numerical that we were supposed to discuss today we'll discuss in the next session. Okay, so after IS method we have DOE method. Like this is a method which is widely used. This is a widely used British method that is developed by UK for designing concrete mixes. Now, what are the benefits of DOE method which makes it a widely used method? So these benefits are: DOE method is simple and systematic, so it uses tabulate values and graphical data for easy designing. Second, it ensures workability and strength, so it balances water content for both workability and strength, and it is based on experimental data. So whatever charts that have been developed in DOE method, it is developed using extensive research and practical experience. So on this slide, I have just summarized the entire step procedure, mixture design procedure for DOE method. So first step is target mean strength calculation, same as we have done for IS code. Second step is selection of W by C ratio. So DOE method provides a graph relating strength to W by C ratio that we use. Third step is selection of free water content. Okay, so free water content is determined based on the required workability that is measured as slump and the maximum aggregate size. So for this, DOE method provides a table for with recommended water content related to these two properties. Fourth step is determining the cement content. So ensure that the cement content is above the minimum requirement of durability. So that is something you need to ensure. And determining the content, it is simple. W by C ratio, you know, and you know the total water content. So total water divided by W by C ratio can get the cement content, and this cement content should be above the minimum requirement criteria of durability. Step 5 is determining the.
Sir, sorry, sir, sorry for the interruption, sir. Screen is not visible. Is it possible to see on screen?
It may be due to some network fluctuation at your end.
No, sir. Network is good, sir. My end network is good. I
Listen,
think you
listen,
are.
listen. It is not a problem on my end. It may be due to your end,
No,
or it may be due to my end. We can't solve that right now. But if it is not
no.
visible, try just to listen. Even though I
Yeah.
will
So
upload
again, my
the.
concern, sir, my concern is when you are recording, it should be visible.
It
After
is
we
visible
have
because
we.
for me I am recording my screen now, so it will be visible to me, and in the
Uh,
recording you will see.
oh,
So just
okay, sir. Okay, sir.
if it is not visible, just wait for the lecture to upload and then you can listen.
Okay, sir. Okay, sir.
Okay. Step 4 is determining cement. Then we have determining the total aggregate content. So this is based on the density of concrete and chosen water to cement ratio. So you will see in DOE method there is a graph which rate density of concrete and water to cement ratio, which helps us to calculate the total aggregate content. Then finally, we will determine the fine and the coarse aggregate proportion. So fine to total aggregate ratio is selected based on the maximum aggregate size, for which DOE provides the graphs for estimating this proportion. So you can see at each step there are certain graphs and curves that has been provided by DOE method. So this is why it makes the design simple and systematic and based on the experimental data. So first, after we have selected the required compressive strength for W by C ratio determination, DOE provides a table and a corresponding figure. So in the table, for a known cement type and coarse aggregate type, we determine the approximate compressive strength that we can get for a W by C ratio of zero point 0.5. Okay, then this strength will go to curve and find this strength, where this strength will lie, and we'll draw a parallel curve, and from that point we'll determine what is the W by C ratio required for our strength. Okay, now right now this may seem to be confusing, so let's take an example. Suppose I want to prepare a M45 grade concrete, and I have OPC type 1, and I have uncrushed coarse aggregate. This is what I know. Okay, so I'm lying in this range, in this row. Okay, so at 20 days with zero point 0.5 W by C ratio, strength will be around 42 MPa. So higher values may be adopted as it is given. So for zero point 0.5 W by C ratio, I may get a strength of 42 MPa. Okay, now what I will do, I will draw a curve line parallel to 42 MPa, and I will see where it interacts with the line which is drawn vertical from point 0.5. Okay, so this is intersecting at this point somewhere. Okay, now from this point what I will do, I will draw a parallel curve like this, passing through this point. Okay, so parallel to the below curve I will draw a curve like this, and on this curve I will check for 45 MPa what W by C ratio will come. So this is my 45. Okay, and on this curve I will see for 45 MPa my W by C ratio will be like this. I can calculate, I can track it down. So it will be close to 0.48 or something. So this is how we use the table and the curve. So we know for 42 MPa I am getting at 0.5 W by C ratio. So I will first draw a horizontal line and a vertical line through 42 and point 0.5 to find where they are interacting. From that interacting point I will draw a parallel curve, and on that parallel curve for my strength that I want, I will point the point of intersection to that curve, and I will backtrack it till the bottom to find the W by C ratio. So my value is coming out around this. So this may be around 0.48 W by C ratio. So this is how we determine from curve what W by C ratio we need to take. We'll see this later on when we do the numerical, so it may be more clear to you. Now, next step is determining the free water content. So for this, we have two tables that are there in DOE British standard. So in the first table, based on the maximum aggregate size and the type of aggregate and the known slump requirement, we get the free water content. Okay, so you can see for different aggregate size and aggregate type and different slump requirement, we have free water content that is mentioned. And in the second table, we have reduction factors mentioned on free water content when fly ash is used. And now why we are reducing water when with increasing fly ash content, you can see the reduction in water is increasing. Why? Because of the ball bearing effect of fly ash. Once we know W by C ratio in free content, free water, we will determine the cement ratio simply by water content upon W by C ratio. Okay. But also we need to check for the durability limits like it is mentioned in this table, which is from BS 18110. We need to check for the durability. So for severe condition, I can have these cover ranges, and I need to have a minimum water content of maximum water to cement ratio of this. And no, for severe it will be this column. Okay. Maximum water to cement ratio 0.55, minimum cement content at 0.325, and minimum grade of concrete as 40 MPa. So this is how we can read this table, and we can check whether the cement content which we have determined is passing the limits or not. After we have determined the total cement content, we will determine the total aggregate content. Okay, so for this, DOE provides a curve to calculate the wet density of concrete when we know the specific gravity of aggregate and we know the free water content. So these two things we know. So from free water content, we'll draw a parallel vertical line. We'll check where it is intersecting towards the specific gravity of aggregate that we have, and we will find the point of intersection by drawing a horizontal line on this y-axis, and we'll get the wet density of concrete. Once we know the wet density of concrete, we can determine the total aggregate content, which is wet density minus mass of cement minus mass of water. Finally, for determining the fine and the coarse aggregate proportion, there are different curves that are provided, which are based on W by C ratio, which is on x-axis, slump value, and my fineness value of fine aggregate. So you can see W by C ratio is there, slump value required is there, and percentage of fine aggregate passing through 600 micron is there. So I have my fine aggregates. I will check how much percentage of my fine aggregate is passing through 600 micron, and I will determine that percent. That is also a factor that they use for proportioning fine and coarse aggregate. So there are three groups of aggregate curves. So this is the first group. Okay, this is for 10 mm nominal aggregate size. This second group is for 20 mm nominal aggregate size, and this third group is for 40 mm nominal aggregate size of coarse aggregate. So in this way, based on your coarse aggregate size, you can take a suitable curve based on the aggregate size, based on the water to cement ratio, and based on the sum requirement. You can find the proportion of your fine aggregate. Okay, so this is how we determine proportions of aggregate, cement, and water based on DOE method. Okay, we have a numerical here for this also. So you may give it a try. Try to solve this numerical on your own. All the values that are required for the solution, it is mentioned here. So give it a try on your own. Else we will discuss in the next session. Okay, how to solve this question. Suppose you are using crushed coarse aggregate, then there will be different sets of value that you need to take. So you can see everywhere it is mentioned. Okay, for ordinary Portland cement, it is mentioned just uncrushed value. So maybe there is no guidelines regarding crushed that is mentioned in the code. Okay, this is maybe this can be one limitation. Suppose for uncrushed and crushed, maybe you can use the same proportion. Later on, you can distinguish them when other values are coming. I will check this table once. Maybe in a updated code, the uncrushed and crushed both are mentioned, but whatever table I found, it was like this. So at that doubt, I will give it a try. Before solving the question, we'll look at that doubt once. Any other doubt regarding DOE method design? How to design using DOE method? So if there are no doubts, we'll conclude this week. One question is pending that we'll discuss in the next session. Okay. So this week we talked about mixture design. We focused on components of mixture design and their relation to desired properties. We discussed IS codes, IS 456 and 10262 for limiting values in step of concrete mixture design. And we discussed DOE method of design, and we saw how to use different curves and charts for mixture design. Okay. Thank you.